Define Q as the region bounded on the right by the graph of g of y equals 3 over y, and on the left by the y-axis for y is an element of the set from 1 to 3 inclusive. Find the volume of the solid of revolution formed by revolving Q around the x-axis. Okay, so before we start into any formulas, let's first just make sure we understand what we are being asked to do, and the best way to do that is to have a picture of the region that we want to rotate. So let's start there, graphing these individual items. Now, if I want to graph g of y equals 3 over y, there's a couple of things I could do. So one thing I could do is, as I mentioned before, take advantage of the ability to work with parametric functions and graph it on the calculator. So if I go under y equals, I just need to set the correct variable to be my independent variable. In this case, the independent variable would be y, and the function x is x equals 3 over y. Well, if y is t, then it's 3 over t. And let me just make sure I'm in the standard viewing window. That looks fine. Now if I graph it, it basically looks like the graph of x or y equals 3 over x, and that is the case. It's basically that same graph. It just so happens, if you kind of look into the algebra here, if you take x equals 3 divided by y, multiply both sides by y, you get x times y equals 3, or y equals 3 over x. So essentially the same function. All right, well that's fine. So the graph here, it looks like I'm going to be entirely in the first quadrant, so I'll just stay there. And the graph that's the part in the first quadrant would look something like this. All right, so that is x equals 3 over y. All right, this region is bounded on the left by the y-axis. Okay, so that's simple enough. That's just x equals 0. And on the range from where y is between 1 and 3. So this is the same kind of notation as y is between 1 and 3, like this. This symbol here means element of, is basically how we read that. So y is an element of this set, or y is between those two values. That's all it means. So y equals 1 is a horizontal line like this, and y equals 3 might look like this. So the region trapped between those parts is right here, and that is going to get rotated around the x-axis, it looks like. So here's my axis of rotation, and I'm rotating around there. So I need to choose first if it's better to use a vertical or a horizontal rectangle. So let's see. A vertical rectangle would actually require me to split this into two different regions. I would have one region that would be a disk and washer, or I'm sorry, a washer method based off of this rectangle here, and then another based off of the curve here. So I think a horizontal rectangle is going to be a better choice. That's going to be parallel to the axis of rotation, which means I would be using the shell method. All right, so the shell method looks like this. The integral from a to b of a length of one general shell times the height of that shell times, and in this case I've chosen horizontal rectangles, so it will be dy for the width. Okay, so let's fill in the details here. All right, so since this variable is y, then my endpoints of integration are functions of y. So I'm integrating from y equals 1 to y equals 3. So that's already set forth pretty easily for us. The length of one shell is the circumference of the circle that each rectangle draws. So a circumference is defined by taking 2 pi times a distance, and it just so happens, of course, and I've already mentioned this, but I'll say it again, the distance from the axis of rotation, that is the radius of the circle. All right, and if that happens to be the x-axis or the y-axis, then it's really just the x or y coordinate of the current rectangle. So this is going to be 2 pi times y. The height of each rectangle, that's going to be this distance from here to here. So we just need to define, what the most positive part of this rectangle is minus the most negative, and that's just dependent upon the function itself, which is 3 over y dy. Okay, and I can see very easily that this y and this y will cancel out, so that will save me typing it in if I'm using the calculator to get my integral. Then also I have some constants that I can pull out here. So 3 times 2 is 6, so that's 6 pi times the integral from 1 to 3 dy. And there's nothing left inside this integral except for if you want to imagine the constant 1 being there. And this is really kind of a special case, and one to make sure you know what happens here, because you can save yourself some time. When you are integrating some integral from a to b with respect to a variable, what happens is when you integrate the function, which is just 1, you tack in an x basically. All right. It gets more complex than that, but that's what the ultimate result is. Then that gets integrated from a to b, and we plug in. So when I plug in b, and then I plug in a, here's what I end up with. An integral of this sort, when there's just a constant function 1 inside the integral, is just measuring the linear distance between the endpoints. Measuring linear distance, I guess what I'm really saying is like vertical distance or horizontal distance, but measuring that kind of a distance is just done through subtraction. So really we can simplify this by now just saying this is 6 pi times 3 minus 1, which is 2, so that makes this region 12 pi. And that's our answer. Then just to give you a reminder as to why the integral of 1 is x, remember you can replace 1 with x to the 0th power, and then when you use your rule of integration, take the exponent, add 1 to it, divide by the new exponent, it becomes x to the 1st over 1, which is why it becomes x. All right, let's move on to the next example, which says to define R as the region bounded above by the graph of the function f of x equals the square root of x, and below by the graph of the function g of x equals 1 over x over the interval 1 to 4. Find the volume of the solid of revolution generated by revolving R around the y-axis. Okay, so let's get a picture. First thing we should always do here. I'll just assume this is probably all in the first quadrant. If I need to extend my graph, I will, but I think that's probably safe here. All right, we have the graph of f of x equals the square root of x. All right, so the graph of f of x equals the square root of x looks something like this. And then the graph of g of x equals 1 over x in the first quadrant looks something to this effect. So there's my g of x, which is 1 over x. And we're on the interval from 1 to 4. All right, so 1 to 4, note that this is an x interval, And the reason I know that that's an x interval without it explicitly stating is because the variable of my function is x. So that's the way that it's implied. Let's see here. I believe this point right here is where x is equal to 1. Because if I plug in 1 to the function g, I would get 1 over 1, which is 1, and the square root of 1 is 1. So the point 1, 1, they're intersecting, so that's that point. So 4, I'll just say, is over here somewhere. And that means we have a bounded region. And that bounded region is right through here. I'll go ahead and shade it in as quickly as I can for you. And what I need to do is rotate this region. That's my region R. I want to rotate that around the y-axis. All right, so rotating around the y-axis, I would need to decide if I want to use a horizontal rectangle or a vertical rectangle. All right, so horizontal rectangle would not be great because the thing is I would have two subregions split by this point. So this region right here would have to be rotated, and then this region up here would be rotated because the rectangle bottom would be defined by different functions on those intervals. So I think that a vertical rectangle is best here. And that's going to be rotated around the y-axis, so it's parallel to the axis of rotation, which means we would be using the shell method. So the volume here is the integral from a to b of the length of a general shell that's formed by rotating times the height of that general shell, and it's going to be done dx because we are rotating, or I'm sorry, because we have a vertical rectangle. Okay, so the endpoints of integration are in terms of x, and I think it's easy enough to see we would go from 1 to 4, so no problems there. The length of each shell, well, the length of the shell is made by rotating this rectangle around the x-axis, which forms a circle, so we need the circumference of that circle. That's the length of the shell. So the length of the shell is 2 pi times its radius. Well, its radius is just the distance that rectangle happens to be from the axis of rotation. And that's always going to be just the value x. Okay, so 2 pi x for the length of each shell. And the height of each shell will come from the height of this rectangle. Now, the example we've done so far have had the rectangle attached to the x or y axes. That's not the case here, but that's no big deal. It's very easy to just, at this point, assume we can come up with the height of this rectangle in general by effectively doing the function f of x minus the function g of x, which is exactly right. So here that would be the square root of x minus 1 over x. And then we would be integrating dx. Okay, now the next thing here is to do the integral. So let's pull 2 pi out, integrate from 1 to 4, x times the square root of x. That's going to be, I'll come up to the side to show you, x times the square root of x is the same thing as x times x to the 1/2 power. And whenever you have two exponential functions with the same base, you can combine them by adding their exponents. So 1 plus a half is 3/2. So this is x to the 3/2 power, and then when I distribute this x, make sure you distribute it to both terms here. X times 1 over x cancels, leaving just 1. Okay, now we do still want to get exact answers. That's always going to be a requirement of the class. And if the final answer is a fraction, we can use fnint to help us get an exact answer without actually going through the steps of the integral. But if it ends up being a square root, which might be the case because we have this square root portion here, then we would just actually need to go through the process. But let's try it with fnint first and see what happens. So if I go to fnint, and I'm integrating from 1 to 4, this would be x. Oh, I'm in the wrong mode. I need to change back to function mode in order for that to give me the variable x here. So x to the 3/2 power. And if you have a calculator that doesn't do the exponents in line like this, just make sure after the little caret symbol, this little symbol right here shows up, just make sure you put the 3/2 in parentheses and it'll do just fine. All right, then -1 dx. Oh, I think we're just fine here actually. So go into change that to a fraction, 47/5, so that means I would have 2 pi times 47/5 by fnint, which gives me 94 pi, I believe, over 5 as my final answer. If you did want to know how to go through the steps here, we're still using the power rule to integrate, but something to the 3/2 power, when you integrate that, so x to the 3/2 dx, you would just raise the exponent by 1, so 3/2 plus 1 is 5/2, and then just divide by the new exponent. So this becomes 2/5 x to the 5/2. And what's happening, it looks like, is these bounds are both perfect squares. So when we take their square root here, we end up with just rational values.